everyone, and welcome to my lab. Are you ready to learn?
Yeah!
Are you ready to have some fun?
Yeah!
Well, let's get started then. I have a small packet here. I'm going to drop it into this plastic bottle, and I want you to pay close attention to what's going to happen. Be on the lookout for fog, for fires, for explosions, for color changes. I want everyone to have a very good time in this very special presentation, marking the 34th year we do this. I'm really proud of that. What I'd like to show you now is that in my lab, we always obey the safety rules. Notice that I have my goggles on to protect my eyes from any splashes. I do this, of course, because it is the state law, and I am a law-abiding citizen. But I also do it for another profound reason. It's good practice. And everyone in my lab practices safety all the time. That's why we have this fire extinguisher ready to be used just in case something goes out of control. We're not planning on anything going out of control, but we have it as a safety precaution. And I'm just going to set it aside here where I know where it is, and everyone else in my lab knows where it is, just in case we need to use it. I'd like to call your attention to this colored glass over here and tell you that expert glass blowers can make beautiful pieces of art using glass. You know, glass is a mixture of several elements. They include sodium, oxygen, there's silicon in there, there's some calcium in there, and glass itself is pretty transparent. Here's a glass test tube, and it is very transparent, but we can add color to glass by adding different chemicals, different elements. This, for example, has the element manganese in it. This color has in it the element gold. This white piece of glass has in it tin. This beautiful glass rod that's green has in it the element chromium. The blue color that you see here is due to cobalt. The yellow color that you see is due to cadmium and selenium. Of course, we use glass blowing for scientific purposes, and I'd like you to take a look at this apparatus that has been made by our expert glass blower. We put colored liquids in it so that it can be more easily seen. It's used for doing scientific research, and our glass blower and all glass blowers can do lots of neat things with glass. I'd like you at this time to welcome our expert glass blower, Tracy Dreyer. Hi, Tracy. Happy to have you here, Tracy.
Thank you.
What do you have?
Well, this is my portable glass blowing station, and this is some of the raw materials that I use to build my apparatus. These are some tools, and then this is my torch.
And how do you get the torch started?
We have a striker, and
Yes.
we just turn on the gas.
What do you burn? What gas are you burning?
This is propane.
Propane. And this is combining with oxygen from the air to give us this yellow flame.
Yes.
But you need the flame to be a little hotter, don't you?
Yes, so that's where I'll add in some oxygen, and you can see the fire getting a little bit bluer.
And the oxygen comes from a tank that you have down here?
Yes.
All right, so this is a hot flame, real hot flame.
Yep, hot enough to melt
Glass?
glass.
All right.
So, would you like me to melt some glass?
Of course, we'd like you to show us how you do your expert work.
I'd like to ask you to put these on.
Put these on? All right, I'll put them on.
So those are a filter. You'll notice as I stick the glass in the fire,
Yes.
you get a yellow
flame. Oh,
flame,
yeah, that's
yeah.
from the sodium that's in the glass. The
Yes,
sodium,
it is.
But we want everybody to be able to see what you're doing.
Exactly.
And so look at the monitor, because the camera has the same filter that Tracy and I have in our glasses.
Yep. So
And
these glasses filter out the sodium and lets us look into the fire and see exactly what's going on.
The yellow flare is not dangerous. It just will not enable you to see what we see.
Exactly.
You can look at it. It's fine if you want to look at it too. So this is a pretty hot flame, isn't it?
Yes.
About how hot is the flame?
This is about 2,500 degrees.
Is that Celsius or Fahrenheit?
Celsius.
Of course,
yes.
in science we use the Celsius, right?
Yep, and so I keep rotating it. You can see it's pretty soft in there. Rotating it, gathering it up.
About what temperature does the glass begin to soften?
Softens at about 850 degrees Celsius.
But I can see that you're holding it very close to the flame and it's not hot, is it?
No, it's not actually. Glass is a very good insulator, and so, yeah, my hands are actually quite close, but it doesn't transfer down the glass. And so you can see I'm just kind of gathering up some glass here. Let it cool.
That's why it's called glass blowing.
So now I'm just going to heat up a little bit more. You have to keep rotating it, otherwise it'll just sag and fall onto my bench top.
That's cool. When you were teaching me how to, and giving me some hints about glass blowing, you told me that we have to be careful about not having stress in the glass.
Exactly. Anytime we heat the glass up enough to melt it, we need to anneal it. And by annealing, what we do is we raise the temperature of the piece, we put it into an oven, and raise the temperature up to 565 degrees for this particular glass. And the stress will leave at that point, and then the oven is cooled down to room temperature slowly so that no new stress is introduced. And at that point, the glass is just like a brand new piece of tubing.
And it looks nice. I wonder, yes. Tracy, can you show us how colored glass is produced?
Absolutely.
All right. You need something that I have for you over here.
Yes. We'll use some cobalt acetate.
Cobalt acetate, you say?
Yes. It's a metal salt. And what I've done is I have a solid rod, and I put a small tube on the very top. And so what I'll do is take a little bit of this cobalt acetate and just put it into the top.
Looks pink to me.
Yes.
It is pink, all right. Now you're going to heat it?
Now I'll heat it. And I have another glass rod. What I'll do is I'll collapse this tube down, and I'll take my other glass rod and mix it up. And this cobalt acetate will then just be mixed into solution. The molten glass is the solution. And you'll also notice that I'm adding a little bit of clear so that my little ball of glass is getting a little bit larger.
Yeah, I can see that. So the cobalt acetate is mixing very well with the softened glass.
Yes. And then when I'm done, I just heat it all the way through, nice and uniform. So now we have a little bit of blue glass.
Very nice. Very nice. Can I touch that?
Yeah, you probably want to wait about 10 minutes.
10 minutes or so
for that to cool down. Yes.
But we still have to anneal it, right? Because if we don't anneal it, we have a lot of stress in the glass.
Exactly.
And you made some small pieces of glass that have stress in them. In fact, these have a special name. Please tell us about that.
These are called a Prince Rupert's drop. They were developed made by Prince Rupert of Bavaria. And how you make these, I take a solid glass rod, heat it up, and let it drip into a bucket of water. And most of them will just break when they hit the water, but some of them survive. And you can imagine that the water cools the outer surface of the bulb, and the inside is still very hot. So there's a lot of stress in these bulbs. And it's quite a dramatic demonstration when we relieve the stress.
All right, let's try to do that. We'll need this piece for background, right? And then we have a
safety cage.
A safety box here. All right.
So normally, this bulb end can withstand the blow from a hammer. But this little tail, if we just introduce a small flaw and snap it, all of the stress that's in this bulb will be released.
So you're going to snap this from that?
Yes, I'll just snap this little tail, and all the stress is going to be released from this bulb.
All right.
You ready?
I'm ready.
I'll count down from 3, 2, 1.
Whoa. That's a shattering experience. Is this safe to touch, or will I be cut?
Absolutely.
Oh,
no, this is quite safe. It's almost like sand. This is, in fact, very similar to the automobile windows.
Very impressive. Thank you very much, Tracy.
You're welcome.
Thank you, thank you. Thank you very much. To do the next experiment, I ask you to focus your attention on what I have in front of me right here, which is a can of carbonated beverage, right? And what does this look like? Yes, you recognize it as a baby bottle. It is a baby bottle, but I have modified it a little bit. In place of the nipple that has the hole in it where the milk comes out, I have replaced that with the rubber bulb from a medicine dropper. This is a very strong piece of rubber. I'd like to show you how strong it is by attempting to inflate it as I blow air into it. Here we go. Cannot do it. It's a very strong piece of rubber that neither I nor you or any other human being can inflate with the powers of our lungs. So I'd like to ask you now to listen to a very familiar sound as I open this can that has in it a carbonated beverage, right? Lots of carbon dioxide dissolved under pressure inside this can. Here we go. Did you hear that? The release of the gas, right? So what I'm going to do is take the baby bottle and pour the beverage in. What do you see? Foam, fizz. You see bubbles, right? What kind of bubbles are those? They're carbon dioxide bubbles. They're coming out of the beverage. I'm going to fill this to the top. And then I'm going to take the screw cap and put it on. Screw it on tightly. What should I do next? You've done this experiment before, huh? So I'm going to shake this, and let's see what happens. And you can see how much carbon dioxide gas is coming out of this carbonated beverage and changing and inflating this very strong piece of rubber that neither I nor any other human being can inflate. So there's a lot of carbonation in carbonated beverages. Of course, you know that because what do you normally do after you take a sip or two of a carbonated beverage? What do? You burp, right? If you do burp, do it quietly and gently, right? You know what the burping is caused by? It's caused by the release of the carbon dioxide gas from the carbonated beverage. So I'm going to now try to release the pressure by opening this gently. What would happen if I open it too quickly? It'll make a mess, right? I'm trying to be careful about not making a mess here. As we release the pressure, there you see everything is open to the atmosphere right now. All right? So at this time, I'd like you to welcome a visitor to my lab. He's been visiting my lab for many, many years. This is a Presidential Award winner for excellence in science teaching from Naperville High School, and now he is at the University of Illinois in Chicago. Please welcome Lee Merrick. Hi, Lee.
How you doing, Bassam?
Doing great. Good to see you again.
It is. I really like your demo. I thought it was kind of swell the way that it expanded like that. And it reminded me of a can of pop like this. When I was a little kid, probably about your age, my dad was sitting in his recliner watching the Cubs lose. Some things never change. He sent me down to the basement to get a can of his favorite beverage. It may have even been this or something different. I was a young kid, so halfway up the stairs, I dropped it. And it rolled the rest of the way down the stairs. But I wasn't very old, and I didn't understand this whole phenomenon that Bassam was talking about, which is really a gas law phenomenon. So I gave it to him. He's leaning back in that recliner, and he opened that puppy up. Notice I'm holding it. That's why I have the safety glasses on.
Yes, that's why I stepped back too.
And he said, "Did you shake that up?" And I said, "No." Remember, he didn't ask the right question. I dropped it down the stairs. Now, what do you do if you think somebody has shaken a can of pop up, or if you've dropped it down the stairs and it has rolled all the way down? What do you do so it doesn't spew on you? That kid's hand went up really fast. What do you do? Tap it. That's right. You can tap it. Now, I don't know if that's some kind of special Wisconsin ritual or not, but if you could get me that hammer there, Bassam, I think we can tap it.
All right.
The ultimate one. Now, you do have to tap it, and you have to tap it smartly. I can do that because my name's Lee. Somebody got it. All right, that's good. Now, what happens there is really Boyle's law. When you shake this can up, you create millions and millions of little bubbles inside the can. When you open it up, the pressure inside the can goes down. That's right. And the volume of those bubbles go up. That's an inverse relationship. So when you tap the can, you dislodge those bubbles so they all go up to the top. So that when you open it now, the pressure still goes down. The volume still goes up, but you don't end up wearing the pop because all the gas is at the top. Do you believe?
I guess I do, yeah.
Okay, good luck. I'll be on the other side.
Where are you going?
I'm over here. After that last incident. Yeah.
All right. So here we go.
Yes.
One. All right.
What I have here, Bassam, is a beaker. Inside the beaker, I have a beaker. Inside the beaker, in the beaker, I have a stirring rod.
A beaker, a stir rod, and
a big honkin' beaker.
Big hunk. All right.
And we're going to ask you to pour this Wesson oil. This is what we call a slick demo inside that small beaker.
Just pour it in there.
Just pour it in there. Just
slowly?
Slowly, fast. Doesn't matter. All right. So we filled up the small beaker. Keep going.
Keep going?
Yeah, keep going. I want you to focus now, your eyeballs, I'm going to move this candle, on the beaker, inside the beaker, and the stirring rod. Oh, what's happening to that beaker? In the beaker. The beaker has disappeared. Can you still see the stirring rod? Yeah. It turns out that the glass in the stirring rod and the glass in the beaker are different kinds. And what's happening here is light happens to have the glass in the beaker and the Wesson oil have the same index of refraction. That means they bend light the same way. So it appears as if the beaker's not there. But this glass in the stirring rod is a different type, and it has a different index of refraction. So it bends light differently, so you could still see that. And we have another one with glass, Bassam, right here.
All right. What do you have here?
I have a little glass vial. And that little glass vial has just one drop of water in it. And I have another one right here.
This vial here has, yeah, I can see it, a small drop of water.
Small drop of water.
Yeah.
And I've got a candle here, and I'm going to light this candle and set it up. And can you get me the other part of this set up that's down there?
Yes, yes.
And we're going to put it inside this safety shield. Okay.
Safety shield.
Safety shield.
What are you going to do?
Well, we're going to heat it up with this candle.
You're going to heat up the sealed bulb that has the water in it?
Right. And we're going to start it boiling. And as it starts to boil, it'll build up pressure. Some of you get a hint here.
I'd like everyone to really cover your ears by sticking both fingers in your ears very tightly.
If you look at the camera, you'll see the water boiling. And then it's increasing pressure inside that little bulb that's sealed. This is sort of like a pressure cooker, except the pressure cooker has a release valve. We don't. Keep in mind, this is one drop of water. Was that loud?
Yeah.
Yeah.
What do we have here, Lee?
Well, here we've got a piece of plexiglass, kind of like a window frame right here with two pieces of glass. This is plexiglass, though, and we're going to fill this up and cause a chemical reaction to occur inside. So you should take number C here.
All right.
And or letter C, and I'll take B, and we're going to pour these in simultaneously, even at the same time. And a chemical reaction will occur. So let's fill that up. Every time we've done this, Bassam has beaten me.
I'm finished.
You are. All right, I'm going to take these out. Now, the first thing we have to do is mix these in here uniformly to cover this up. So I don't know if you could see that. Now, then we're going to have to add one more chemical to this. We've added so far something called sodium hydroxide, which you may know as Drano.
And what else?
And we've added silver nitrate. Now we're going to add some sugar. This is the sweet part of the demo. And then we're going to coat the inside with that. And as we do that, we'll get what's called a redox reaction occurring, oxidation reduction. What that means is that the sugar will be oxidized and the silver will be reduced. What that means is we'll be coating the outside of this with silver. And when you look at it at first, it'll look black because we're coating very thin layers of silver on. You're going, oh, cheap trick, where's the silver? Eventually, we'll put enough atoms of silver on so it will start to look silver-like. I think it's happening now, at least it appears to be. That's no reflection on you people out there yet. All right. How's it look? It's looking good? It is? Bassam, you want to see a real handsome guy?
Yeah. So this is how silver mirrors are made.
This is one way you could make silver mirrors.
Thank you very much,
Okay,
Lee. Thank you very much. Thanks. So I'd like to thank you for coming to this very special presentation. I want to also to remind you to always enjoy the experiments that you do. And remember, no matter what you do, science is fun. Thank you very much, everyone. Thank you.
Do you want to try some fun experiments at home? Well, they're only a click away. Check out the Science is Fun website at this address, www.scifun.org. You'll discover fascinating facts about chemicals and other great science information.